Covariance and correlation both inform us about the relationship between two data series. And while correlation is the value we end up being more interested in because it's a more helpful metric, we have to calculate covariance on our way to correlation, which is why we want to start with an understanding of covariance. So the covariance formula, we'll start here and then unpack it piece by piece. But the covariance formula, this says that the covariance between two series given by x and y is equal to, and this right-hand side basically just says the mean of the square areas that are given between each particular data point x sub I, y sub I, and the mean data point x bar, y bar. Equivalently, we can write this formula this way. So these two formulas represent exactly the same thing, they're just written in different ways. This second formula here tells us that covariance can also be calculated as the mean product. So if we multiply each x sub I by its corresponding y sub I, and then we take the mean of those products, we get this value here, and then we subtract from that the product of the means. So the mean of all of the x sub I values, the mean of all the y sub I values, and we multiply those two products together to get the product of the means. We subtract that from the mean of the products. This is another way to calculate covariance. So when you see these two different formulas, they mean the same thing. Now, to understand covariance, what we really want to realize is that this first formula looks a lot like the variance formula that we learned about earlier. To get back from this formula to the variance formula, what we want to do is replace y with x. So we would say the covariance of x with itself, 1 over n times the sum of I equals 1 to n of x sub I minus the mean times x sub I minus the mean, because again, we're just replacing y with x here. And then we can see that we can rewrite this right-hand side as the square of this single binomial, because we have two identical binomials multiplied together here. So instead of saying x sub I minus x bar times the same thing, x sub I minus x bar, we can rewrite that as x sub I minus x bar quantity squared. And we should now recognize this as the variance formula for the variance of x. And so because these right-hand sides are equal, what we're essentially saying here is that the variance of a single variable x is equivalent to the covariance of that variable with itself. Given that relationship, if we sort of work backwards from this idea of variance, so thinking about variance, if we almost just think about a one-dimensional number line, and we have some data set, some data series given by this x variable, and we say that the mean of that series is here at x bar, when we want to calculate the variance of this variable x, what we do is we look at all of the other values of x in the data set. So let's say that there's another value of x in the data set right here, and right here, and right here. And what the variance formula calculates is the mean of the square areas that are generated when we make a square out of the distance between each of these data points and the mean. So in other words, looking at this closest data point here, if we create a square between this data point and the mean, and then we create another square between this data point and the mean, and finally another square between this data point and the mean, now we have three pieces of area. This green square is the largest amount of area, then the white square, and then the blue square is a smaller amount of area. What this variance formula gives us is the mean amount of area of these three squares, or the average area. So let's say that this little blue square, let's just make up values. Let's say that this little blue square has a square area of 1 square unit. Let's say that this white square is a square area of 4 square units, and the green square is a square area of 5 square units. What we would do is add up all of these areas. So 5 plus 4 is 9, plus 1 is 10. The total area of all three squares together is 10 square units. And then we have 3 data points, so we would divide that by 3. We get about 3.33. And so the variance of the x variable here, if this is the data set, is about 3.33. This is what we calculated in the past, the variance of just one variable x, which we now know is also equivalent to the covariance of x with itself. But instead of calculating the covariance of x with itself, if we instead want to calculate the covariance of x with a different variable y, now our little two-dimensional picture has to transition to a three-dimensional picture. So in that three-dimensional picture, instead of plotting values of just x along this one-dimensional line, we would plot xy coordinate points in a two-dimensional plane. So instead of just now along a line where we have this mean value of x here, and then we have this point x sub 1, x sub 2, and x sub 3, now we have coordinate points where maybe this first point here is the point x1, y1, and this point up here is the point x7, y7. But each of these is just one value from the x data series paired together with its associated y value from the y data series and then plotted in the two-dimensional plane. Now, what we already know for this series, instead of having just a mean x bar for the one series in x, when we find a mean for x and y together, what we're doing is we're averaging all the x values and we're averaging all the y values, and then we are plotting that mean point, and this point is x bar, y bar. It's the mean of all the x values and the mean of all the y values, and we plot that point. And we can think about this as the balancing point of the entire data set. Then, just like when we had variance in one variable, to show covariance with two variables, we just look at the sum of all those square areas. So if we plot some of those square areas, we connect each individual point to that mean point. So we did that here with this point. Here with this point, we found this smaller square area. With this point up here, we found a smaller square area. And then with this last point up here, one of the bigger square areas. So we plot all those squares. If we add up all of the areas of all the squares connecting each point to the mean, then we get this whole sum right here. When we divide by n, the number of data points, that gives us covariance, which is just the average of all the square areas. So this covariance concept is just like the variance value we learned about earlier, except that in this way, we get to see how x and y vary together. We're not just looking at one variable on its own. Instead, here, we're looking at the two variables in comparison to each other. And we can sort of imagine here how both x and y have an effect on the variance. This is our mean point, but if we picked a point, let's say, way up here, way above the mean, but not too far to the right of the mean, and then we created this rectangular area between that point and the mean point, maybe that looks something like this, we can see how this area might actually be quite large because of the amount of variance in y between this particular point and the mean, even though the variance in x for this particular point is small. The fact that the variance in y is larger lets us see that this point actually varies quite a bit from the mean, even though the variance in x is small. If we were just looking at one variable alone, just the variance in x, this point wouldn't look like it varied that much from the mean at all, because it's only this tiny little width right here that constitutes the variance in x. But this huge height gives us the variance in y, and so we can see that this point actually varies quite a bit from the mean. And so it's that covariance, being able to see what's happening to x and y at the same time, that allows us to see more than just this one variable picture over here. Now, when we calculate a value for covariance, it will help us to see the relationship between the two variables x and y. For instance, with this particular data series here, we can actually sketch a line through the data, and we'll talk more about this later, but sketch a line through the data that shows us that there's a positive relationship between x and y. It's positive because as x increases, so as we move to the right along the horizontal axis, as x increases, y also increases. We move up along the vertical axis. Or we could work backwards and say that as x decreases, so as we move from right to left this way, y also decreases. We move from top to bottom. So either y is decreasing as x is decreasing, or y is increasing as x is increasing. In either case, both variables are moving in the same direction at the same time. that's what we call a direct relationship or a positive relationship. If we have instead a relationship moving in the other direction, so if our line looked something like this instead, maybe like this, that would indicate an inverse relationship or a negative relationship, because as x is increasing, so as we move from left to right and the value of x increases, the value of y decreases. We're moving down along this line as x increases. Or working in the other direction, as x decreases, so as we move from the right to the left, as x decreases, y is increasing. And so the variables are moving in opposite directions, and we call that an inverse or a negative relationship. The value of covariance will give us that general direction of the relationship between the two variables. If covariance is positive, that means there's a positive direct relationship between x and y. If covariance is negative, that means there's a negative or inverse relationship between x and y. So if covariance is positive, the variables generally are moving in the same direction. If covariance is negative, the variables in general are moving in opposite directions. For that reason, covariance is a helpful metric. The problem is that it doesn't tell us the strength of the relationship, only the direction of the relationship. And it's not a standardized value, so changing the scale of our data will change the value of covariance. One of the ways that we can see that is by simply adding one data point to this existing data set. So we had all of these little blue points in our data set, and they're all on or very close to this line running through the data set. And we would calculate a covariance by finding the mean of all of these different square or rectangular areas. But if we add another point to our data set, and let's say that it is directly along this line right here, even though this point is right in line with each of these other data points in the set, this point, this point, this point here, here, and here, we're all right along this line, and so is this new point, such that this new point isn't adding really any new information than all of these other points here. It's right in line with all of the other values along this line. But if we sketch in the area created between this point and the mean right here, we can see that this massive amount of area is definitely going to increase our covariance calculation, even though this particular point doesn't really vary off of this trend line in either the x or y direction. And we could continue adding points directly along the line way out here in space, and that huge area is going to contribute to increasing our covariance value, even though we're not really seeing any variation in the set. Essentially, all we're doing is scaling up this sum right here, which means that we calculate a larger total area, and that tells us that our data points are creating a large amount of area away from the mean point, but it doesn't give us any indication about how close or far our data points are from this trend line. And that's what we're really interested in. We want to know if all these data points that we're adding to the set are right along this trend line or far from it. This point we added up here was right along the trend line. We want to be able to distinguish between that kind of a point and maybe a point down here that is far away from the trend line. And that's what correlation is going to allow us to do later. But for now, despite all of its problems, let's just look at an example so that we know how to use this formula to calculate covariance now that we know what it's doing. We can obviously do this by hand or with a calculator, but these kind of calculations, especially as our data sets get larger and larger, are much, much easier to do with software. So for instance, here's a table, and these are the values in our X and Y series. So we have our X values here, 1, 2, 3, 4, 5, 3, and 4, and their corresponding Y values, 2, 4, 6, 8, 10, 5, and 9. So essentially, these are all of our X sub I and Y sub I values. And then we need to find the mean X bar and Y bar. So we sum the entire X series and the entire Y series, and we get sums of 22 and 44 respectively. And then because there are 7 data points, because n is 7 in this case, we divide 22 and 44 by 7 to get the mean. So this here is X bar, and this is Y bar. And in fact, these series are what was represented here in this original data set of blue points in the plane. So we calculate the mean of both the x series and the y series. Then we need to calculate these x sub I minus x bar values and the y sub I minus y bar values. So that's where we go next. We have x sub I minus x bar. So this first value here is 1 minus the mean of x, 3.14, etc. This second value here is 2 minus the mean. This is 3 minus the mean, etc. And then same thing here for y. We take y of 2 minus the mean of 6.28 to get this negative 4.28 value. In this second row, we take 4 minus the mean, we get a negative 2.28. So we calculate all those y minus y bar values. So we calculate all those y sub I minus y bar values. And then, of course, we take their product, because here we have to multiply these x sub I minus x bar values by the y sub I minus y bar values. So once we have these products, we then add them all together. This sum here says to add all those products together. That's this sum right here. So when we add everything together, we get 22.7 approximately. And then we just divide this value by 7 to get the covariance of x and y as approximately 3.2449. This is a rounded value here, but this is the covariance of x with y. And like we said at the beginning, this second formula here will do the same thing. All we do once we have our x and y values, we take the product of each x and y. So here we have our values for x, our values for y. So if we multiply 1 times 2, we get 2. 2 times 4 is 8. 3 times 6 is 18. 4 times 8 is 32, etc., all the way down to 4 times 9 is 36. So if we multiply all the x and y values, we find all these products. So this here is the xy column. And then we take the mean of these. So we add all of these together, and then we divide by n equals 7, the number of data points we have. So if we add all these together and then we divide by 7, the result we get is this mean of the xy products, which turns out to be 23. And then we just subtract from that the product of the two means, which we already have. We already have x bar and y bar. You can see here we have about 3.14 and 6.28. If we multiply these values together, we're going to get about 19 3/4. And so when we then take 23 here minus the product of x bar and y bar, which is about 19.75 roughly, the value we end up with is about 3.25, or more specifically, this exact value here for covariance, 3.2449, if we round to the first 4 decimal places. So these two covariance formulas do calculate exactly the same value, just in 2 different ways. And so, just to tie this covariance back to this data set we started with, the fact that we get a value here of 3.2, the fact that it's positive, tells us that there is a positive or direct relationship between x and y, meaning that as x increases, y increases, or as x decreases, y decreases. And we see that with this rough trend line that we sketched through the data. If we had found a negative value for covariance, it would indicate the opposite relationship between the x series and the y series. It would tell us that there was more area over here in this direction, down here or here, along this negative trend line, than there was area in this direction along the positive trend line. So really the biggest takeaway here is that when we find a positive covariance value, it means we have a positive or a direct relationship, that the variables change in the same direction instead of in opposite directions. And next, we're going to look at how to use what we've learned about covariance and standardize it into correlation, which will be an even more useful measure for us.